Good morning, everyone. How does this work? Like this. So as you know, and as underlined earlier by Alban, the clinical use of 4D flow MRI is still hampered by long scan times on the order of 5 to 15 minutes for aortic applications, as well as the lack of multi-center data. A recently developed compressed sensing-based sequence by Liliana Ma and collaborators at Northwestern University and Siemens have shown scan times on the order of 2 minutes, which provided aortic velocity and flow rate indices within 13% agreement when compared to a conventional technique. This was a single-center study at 1.5 Tesla, performed in 20 healthy volunteers and 11 patients. The aim of the current work was to further extend this feasibility study, including more patients at the first center, also include another center at 3 Tesla, and then to investigate the ability of such sequence to provide accurate wall shear stress measurements. So subjects were prospectively included at both Northwestern University in Chicago and University of Calgary. Data at Northwestern were acquired on a 1.5 Tesla scanner in 25 healthy volunteers and 26 patients with aortic and/or aortic valve disease. Data in Calgary were acquired on a 3 Tesla scanner in 10 healthy volunteers and 10 patients with different conditions. Each subject underwent 4D flow MRI using 2 techniques. First, a conventional approach, which was acquired according to the current recommendations, including a GRAPPA technique with an acceleration factor of 2, and the compressed sensing sequence was acquired with an acceleration factor of 7.7. Both were using retrospective ECG gating and were matched for spatial resolution and temporal resolution, as you can see here, as well as encoding velocity. 4D flow MRI data analysis for each dataset included first preprocessing to correct for eddy currents and velocity aliasing and noise. Then the aortic 3D volume was segmented using a convolutional neural network approach that was previously presented during this conference. And then we computed peak systolic maximal velocity in 3 regions of interest in the ascending aorta, the aortic arch, and the descending aorta using a custom software based on velocity maximal intensity projections. Wall shear stress was then computed using a 3D approach that was previously described in 6 regions of interest throughout the aorta, along the inner and the outer wall of the ascending aorta, the aortic arch, and the descending aorta again. So first of all, the compressed sensing sequence confirmed significantly shorter scan times when compared to the conventional 4D flow sequence on the order of 2 minutes at Northwestern on the 1.5 Tesla scanner, and the order of 3.5 minutes at Calgary. And this was due to the fact that their protocol further included whole heart in the acquisition volume in addition to the thoracic aorta. Now I'm just showing a few representative examples of the data we obtained. First, in a patient with a dilated aorta at Northwestern. You can see here the velocity maximal intensity projections obtained using the conventional sequence on the left and the compressed sensing one on the right, and the same for the wall shear stress 3D vectors throughout the aorta. This is a patient from Calgary who had a bicuspid aortic valve and ascending aortic aneurysm. Again, the velocity maps are shown on the left and the wall shear stress on the right, comparing the conventional and compressed sensing 4D flow maps. You can already appreciate that we can observe some underestimation when using the compressed sensing technique when compared to the conventional one. And this was confirmed in our statistical analysis over the whole subgroup group. I apologize in advance for this slide because it's very busy. I'll walk you through it. So this is the data from Northwestern, healthy controls on the left and patients on the right for the peak velocity in the ascending aorta, the aortic arch, and the descending aorta. You have for each index the values averaged over the groups when using the conventional technique and then the compressed sensing CS one, as well as the percentage difference between the 2 methods. And then the same for the wall shear stress in the different aortic regions of interest. and the same for Calgary data in healthy controls and patients. So as you can see, as denoted by the bold font, most indices were significantly underestimated by the compressed sensing 4D flow when compared to the conventional one, and this was down to 15% for peak velocity and 18% for wall shear stress. So to conclude, compressed sensing aortic 4D flow MRI was feasible at both 1.5 and 3 Tesla, enabling significant and substantial acceleration. However, it did underestimate velocity and wall shear stress when compared to a conventional technique, and the agreement remained within 18%. So we think that further work and larger studies are still needed on more homogeneous patient groups to be able to study the clinical value of such technique. I just wanted to add that this was part of a multi-center effort initiated by Dr. Markle on the feasibility of such sequence, and we hope that such a multi-centric effort will be pursued in the future to be able to assess the clinical value of 4D flow MRI. And with that, I would like to thank all my collaborators and thank you all for your attention.